Hello, everyone. Today I'm excited to present our recent findings from the 2025 IEEE 16th Control and System Graduate Research Colloquium, ICSGRC. Our presentation is titled 5G Performance Evaluation in Thailand through Stationary and Drive Testing. Our study provides a comprehensive comparison of 5G network performance from two major mobile network operators in Thailand. The primary objective of our research was to evaluate how these 5G networks perform in real-world environments, especially following a significant merger that involved one of the providers. To begin, let's discuss why 5G technology is so crucial. 5G offers high-speed, low-latency, massive device support, and stable connections. These features enable a wide array of new applications like smart cities, telemedicine, autonomous vehicles, and industrial automation. Achieving this performance involves advanced technologies: millimeter wave, massive MIMO, beamforming, network slicing, edge computing, and carrier aggregation. A robust 5G network is essential for seamless internet usage, especially in high-traffic areas like shopping malls. Our research focused on evaluating 5G efficiency in Mega Bangna, a well-known shopping center in Thailand, to provide critical insights for both users and providers in real-world environments. Our study focused on two prominent mobile network providers in Thailand. First, OperaX, a leading communications and digital technology provider established in 1986. Their core business includes mobile, home internet, enterprise, and digital services. Second, OperaY, another major telecom and technology company. A key aspect of OperaY is its recent reorganization in Q1 2023 through a merger of two mobile operators. Their main services are mobile, high-speed internet, and pay TV. OperaY also invests in digital ventures like IoT, AI, and cloud computing. This recent merger involving OperaY was a significant motivator for our research, addressing a gap in updated comparative studies. Our study utilized two identical 5G Android smartphones, Snapdragon 695, 128 gig ROM, 8 gig RAM. The same models used in prior studies. Each phone had a prepaid SIM with unlimited data from one of the two major Thai 5G providers. For performance testing, we used two key software applications: Ookla's Speed Test, version 6.0.2228290 for stationary tests, and GNet Track Pro, version 32.4 for drive tests. This tool selection aligns with similar research. All collected data was then meticulously processed and analyzed using Microsoft Excel, where we performed both descriptive and inferential statistical analyses to derive our findings.
Next, let's detail our stationary test methodology. These indoor tests were specifically conducted at Mega Bangna, one of Thailand's large-scale shopping centers. The testing period was from 7:10 p.m. to 8:50 p.m. The primary goal of these stationary tests was to evaluate download speed, upload speed, and latency under indoor conditions. We randomly selected a total of 26 test points on the second floor of the building. While 26 measurements were collected, we used 24 for our final analysis, as the highest and lowest values for each parameter, download speed, upload speed, and latency, were excluded as outliers to ensure data quality. The remaining data were then thoroughly analyzed to assess the network performance across these three parameters. An example of the speed test application used for these stationary measurements can be seen in Figure 1A on our slides. Following our stationary test, we proceeded with a drive test to evaluate network performance in a mobile scenario. This test began near Mega Bangna at approximately 9:15 p.m. and concluded around 10:15 p.m. at Ratchadam known Nok Road, located in the heart of Bangkok. For these drive tests, we utilized the GNet Track Pro application. This application allowed us to continuously collect crucial signal quality metrics along the route, including reference signal received power, or RSRP, reference signal received quality, RSRQ, and signal-to-noise ratio, or SNR. An illustration of the GNetTrack Pro application interface during our drive test can be seen in Figure 1B. It's important to note that any data recorded while the vehicle's speed was zero, such as at traffic lights or during stops, was excluded from our analysis. This was done to ensure that our results accurately reflect the network's performance during actual mobile usage. By conducting both stationary and drive tests, we aim to provide a comprehensive assessment of 5G network performance across different real-world conditions. Moving on to the core results of our stationary tests, conducted at Megabangna Shopping Center. This slide presents a comparative overview of key performance metrics for both OPER-X and OPER-Y. For download speed, OPER-Y demonstrated a higher average of 360.57 megap compared to OPER-X's 252.04 megap. This difference was statistically significant, with a p-value of 0.003, indicating that OPER-Y clearly outperformed OPER-X in this aspect. Conversely, when it came to upload speed, OPER-X showed superior performance, achieving an average of 71.59 megap, while OPER-Y recorded 30.56 mpp. The p-value of less than 0.001 confirms this as a statistically meaningful difference, with OPER-X excelling in upload speeds. Finally, for latency, OPER-Y had a numerically lower average of 17.77 milliseconds compared to OPER-X's 23.82 milliseconds. However, the statistical analysis, with a p-value of 0.084, revealed no statistically significant difference between the two operators at this location. This could be attributed to the high variability in OPER-X's latency values. In summary, the stationary tests highlighted clear distinctions in speed performance, with each operator showing a unique strength, while latency remained comparable. Now, let's look at the results from our drive tests, which focused on signal quality metrics as we move through the city. First, for RSRP, or reference signal received power, OPER-X showed an average of minus 71.33 dBm, while OPER-Y was very close at minus 72.19 dBm. Both of these values fall within the excellent category for signal strength. OPER-X had a slightly higher RSRP, indicating a marginally stronger received signal on average. Next, we examined RSRQ, or reference signal received quality. Here, OPER-X had an average of minus 11.70 dB, and OPER-Y was nearly identical at minus 11.67 dB. Both are considered to be in the good range, indicating similar signal quality performance for both operators during the drive test. Then for SNR, or signal-to-noise ratio, OPER-X measured 15.22 dB, and OPER-Y was slightly higher at 15.77 dB. Both of these values are categorized as excellent, suggesting that the signal was strong relative to the background noise for both networks, which is crucial for clear and stable connections. Finally, regarding the 5G non-standalone NSA connection rate, OPER-X maintained a 5G connection 99.15% of the time, slightly higher than OPER-Y's 97.20%. The remaining small percentage of connections for both operators were on 4G LTE. This indicates that both providers offer a very high percentage of 5G connectivity even in a mobile environment. Overall, the drive test revealed that both OPER-X and OPER-Y provided comparable and strong signal quality throughout the test route with very high rates of 5G connectivity. In conclusion, our 5G evaluation revealed distinct strengths for OPER-X and OPER-Y. OPER-Y excelled significantly in download speed, highest in similar Thai studies, and showed a trend towards lower latency. Conversely, OPER-X demonstrated superior upload speed. For signal quality during drive tests, both providers delivered comparable and robust performance across RSRP, RSRQ, and SNR metrics, indicating similar signal strength and stability on the move. These findings offer valuable insights. For end users, they aid in choosing a network aligned with their priorities. For service providers, they highlight areas for competitive positioning and improvement. We acknowledge study limitations, including specific test locations and timing biases. However, our research provides a valuable snapshot of 5G performance in real-world Thai conditions. To build on our findings, future research will focus on three key areas. Firstly, we aim to explore 5G standalone SA networks, moving beyond the non-standalone NSA focus of this study. This will allow us to assess specific improvements in latency and reliability critical for advanced 5G applications. Secondly, we plan broader geographical testing, expanding beyond this urban area to include rural and other high-density environments. This will capture a wider range of environmental variability and understand network performance differences across locations. Finally, we will implement long-term data collection. Gathering data over extended periods, different times, and varying conditions will provide deeper insights into network consistency and stability, offering a more dynamic understanding of the 5G user experience. These future endeavors will significantly complete the picture of 5G capabilities and inform further development and deployment strategies in Thailand. Thank you all for your attention to our presentation today. I hope our findings have provided valuable insights into 5G performance in Thailand. Now, I would be happy to answer any questions you may have. Please feel free to ask.